Okay, good morning, class. Again, you'll have to be looking at me from this side as I look at my big screen over here. Hope everybody's well. We're going to be doing chapter 6 today. I'll try to do half of it, and I'm sorry about the visual noise. I really don't know what to do about that. All right. So let's get started. As always, I have to open up my screens, and there's really no way to get all these screens open before you guys come aboard, or at least no way that I figured out how to do it. So if you want to fast forward these 2 or 3 minutes till you see me clicking around on the screen, that'll be fine. So first thing I do is share my screen. Share this screen. You should be seeing that smaller screen. I'm going to put it down in the lower right hand corner. Now I'm going to start opening up screens. Okay, so let's go into Thermo. Let's go to instructor resources and open up the presentation slide for chapter 6. All right, and I'm going to make sure that my screen is being shared properly. Looks like it is. So I'm going to start bringing up some other files. Let's see. Oh, I want to open OneNote in case you want to do a little scribbling on my board. OneNote. And I'm going to open, let's see, we need to get the tables out in case we need those. Okay, so get OneNote back up here. All right, I'm going to check my share again. Looks like you've got everything. So if I can find PowerPoint back in there. Okay, there's PowerPoint. All right, chapter 6. Here we go. We're ready to start chapter 6. Entropy. Entropy is a property. It's a little bit different from the others. To summarize entropy, like I said, is a property like enthalpy and internal energy, some of these other things. But the thing about entropy is closely associated with heat transfer, and it is a key measure of work process efficiency. All right, so here we go. And learning outcomes, of course. And again, we talk more about what entropy does, how to transfer it, how's it created, we don't talk about exactly what entropy means. To me, entropy is sort of a measure of how much we're warming this earth in our processes. And we'll see that later. All right, so we're going to learn how to evaluate entropy, and especially entropy change between two states, and analyze isentropic or constant entropy processes. Now, I will warn you, I'm going to go in by the slides pretty straight today. If you'll hang with me in there, I'll make a deal with you. I'll give you some homework on chapter 6 that'll be really interesting to you, I believe, and won't be as quite as monotonous as these slides. All right. We're going to talk about heat transfer as an internally reversible process, and it's the area under the temperature entropy diagram. We'll talk about by the way, the symbol for entropy is S. Capital S is total entropy, like always. Lowercase s is specific entropy, and the units of entropy are kilojoule per K. And for specific entropy is kilojoule per kilogram K, and same in comparable English units. One of the most important things that I believe concepts of entropy, not only entropy production, the fact that all cycles tend to produce entropy. They don't reduce entropy. They all increase entropy, because so we could say that all thermodynamic cycles tend to increase the entropy of the earth, and that's where you could get into the global warming connection, although we won't talk about that very much. Isentropic efficiencies of turbines is another thing we want to get out. So the main things we want to get out of here is entropy is very closely associated with heat transfer. Entropy, all not processes now, but cycles tend to increase entropy. And isentropic efficiency is a really good way to measure the performance of a work-producing machine or work-requiring machines, such as turbines, compressors, and pumps. So entropy is very similar to mass in that it is a mass and energy. It is another extensive property. Although lowercase entropy, entropy per pound or entropy per kilogram, is a intensive property. Just as mass and energy are accounted for by mass and energy balances, we also do an entropy balance. And by the way, entropy is in the tables. It is the last property that we'll be learning about. And like mass and energy, entropy can be transferred across the system boundary of a control volume system. If you'll remember from last chapter, we had this Clausius inequality, which says that the cyclic integral of the heat transfers over their temperatures is equal to this minus sigma. And sigma is a measure of, actually it's a measure of entropy creation. This integral here looks pretty difficult, but it's not. In our steady state systems we study, it's quite straightforward, as we'll see. But we saw for this sigma cycle, by the way, to me it would have been easier to put a minus sign on the left side of this equation and show sigma as a positive on the right side. It looks a little more conventional, but anyway, minus sigma is fine. When we solve this equation, which we will for sigma, we'll find if sigma equals 0, there are no irreversibilities present. It's a reversible system. It's as good as a system gets. And it's never really achievable in practice, but according to the second law of thermodynamics, it is possible. If we get sigma, the cycle, which sigma again is essentially one measure of entropy. If entropy is less than 0, this is the common case. This is what happens in everyday cycles. Irreversibility, such as heat transfers, friction effects, leakage effects, all kind of irreversibilities are present, and that's the way all real world processes go. If we do an analysis of apply the Clausius inequality and come to that up with the sigma of the cycle is less than 0, then you violated the second law of thermodynamics, and that's never been done before. So we term that impossible. This diagram, if you just follow it, shows that that entropy is a reversible process. So let's look at it. Consider these two cycles. Process A, you go through A to come back C. And process B plus let me start that over. Process A plus process C. So we go for process A, go back to process C. These are two reversible processes. So look at process B plus process C. So we go through process B, and we come back process C. So if we apply equation 513, that's the Clausius inequality, we find the integral over process A plus the sine integral over process C is equal to minus sigma. It's equal to 0 because they're reversible. If we go to process B and C, we have process B, the integral, plus process C integral is equal to 0. So what we can do is if we subtract these two equations, we have the integral of process A is equal to the integral of process B. So what that says is both process A and C and both process B and C are arbitrary internally reversible process linking states 1 and 2. So it follows that the value of this integral is independent of the particular internal reversible process and depends only on the end states. That's a big thing, that the entropy changes only depend on the end states and not the process, not the path. All right. If we recall from section 1.3.3 that a quantity is a property if and only if its change in value between two states is independent of the process. Okay, so we just, in a lightly mathematical way, prove that. So we can say that entropy is a property and is represented by a capital S. And S, the change, and again, like enthalpy and internal energy, generally we talk of entropy as the change in entropy. And the change in entropy from state 1 to state 2 is equal to the integral from 1 to 2 of delta Q over T of an internally reversible process. Where the subscript internally reversible here signals that the integral is carried out for any internally reversible process linking states 1 and 2. It's not path dependent. It is endpoint dependent. Don't worry too much about that equation if you don't understand it. It's easier applied than it is maybe to describe. Hang with me. So equation 6a, that's what we were looking at, right? Okay, it states equation 6a allows that the change in entropy between two states to be determined by thinking of an internally reversible process between two states. But since entropy is a property, that value of entropy change applies to any process between those two states, internally reversible or not. In other words, internally reversible or irreversible, which all real world processes are irreversible. So that equation holds for irreversible everyday processes. The entropy change is introduced by the integral equation 6.2a, for which no accompanying physical picture is given. So what they're saying is there's no physical picture of entropy. It's a concept. You can apply it and use it, but being able to visualize it in the palm of your hand is too abstract. Still, the aim of Chapter 6 is to demonstrate that entropy not only has physical significance, but is also essential for thermodynamic analysis. All right, I'm going to start my stopwatch here. Start watch and make sure I don't go too long. All right, now I'm going to check my share and make sure my share is good. Because I can't, okay, you should be seeing my screen. All right, next slide. Now, don't give up on these slides. The actual application of entropy to real world problems is pretty straightforward, and it's just plain interesting. For me to be able to explain to you what entropy is, to show it to you, to feel it in your hands, I can't do a very good job of that. All right. Okay, I didn't go down, did I? All right, now I should go down to 10. Okay. All right, entropy is an extensive property, and I don't like it when he says that because specific entropy is an intensive property. But like any other extensive property, the change in entropy can be positive, negative, or zero. By inspection of 6.2 equation, the units of entropy are kilojoule per K, degrees Kelvin, and interestingly, as I mentioned many times, there's no degree symbol outside of the symbol Kelvin, not sure why. And BTUs per degrees R in the English system. Units for energy, kilojoule per K, BTU per degrees R. Now, specific entropy, which is an intensive property, they use a little s. And I make a big S and a little s. They look a lot alike. So I'll try to make sure you don't get confused by those. So specific entropy follows as kilojoule per kilogram K in the metric system and BTU per pound mass degrees R in the English system. Okay, entropy, the equations of entropy are just exactly like the equation, or the same structure as the equations for enthalpy and internal energy and specific volume, in that when you have a mixture, the quality equations apply. For instance, this equation is identical to the quality equation for enthalpy, internal energy, and specific volume. It's just we're now using the small s's for the entropy, where S is F is the entropy of saturated fluid. SG is the entropy of the saturated, no, SF is the entropy of saturated liquid. SG is the entropy of saturated gas, just like before. And for a two-phase mixture, temperature and pressure, okay, down in the liquid area where we sometimes can use the compressed liquid tables, which aren't very extensive and not very easy to use. In the liquid area where it's really sort of hard to look up in the table, you can approximate and very closely, by the way, the entropy of a liquid for liquid water as by looking up SF of the water at that temperature. So if you got a temperature of say 40 degrees and a pressure of 5 bar or 2 bar, whatever gives you a nice liquid pressure, liquid state, then you can just look up go to the temperature of 40 degrees, I believe that's what I said, and look up S of F, and that's very close to the entropy of both the temperature and the pressure at that point. We discussed that in chapter 3. I talked around that a lot. I hope you understand. Okay, and now we got two pretty, what would we call it? Robust looking diagrams here. This is temperature entropy diagram. You can see the lines of constant pressure go exactly like they did on the temperature specific volume line. You've just replaced specific volume with specific entropy. There's also a chart of enthalpy versus entropy, but quite frankly, I've never used this one very much. Temperature versus entropy diagram is now going to be our predominant way of drawing our diagrams for the rest of the thermodynamics, T and S. And we see that the pressure lines are pretty much like they were with T and V, so it's not going to be a hard transition at all. Now, as I said before, entropy change is closely associated with heat transfer. Entropy changes when you have heat transfer. That's fine. Where entropy is not such a good thing is the entropy changes during turbine processes or compressor processes. We'll talk about those later. If we look at equation here on this slide, equation 6.2, the defining equation for entropy change on a differential basis is ds equal dq over t. And we can usually integrate this thing because we're looking at steady state. So del Q becomes Q2 minus Q1. And the temperature, if we're dealing with a constant temperature, such as a TH or a TC, we can solve this equation whenever we need to and work in a problem. So equation 6.2 indicates that when a closed system undergoing an internally reversible process receives heat by energy, the system experiences an increase in energy. Okay, well, here's what he means. As you know, when a system is receiving heat, that's positive heat, the way we define the polarity of heat. Positive coming in, negative going out. So if the heat's coming into the system, this term is positive. Temperature is always positive, so the ds is positive, and the entropy increases with positive heat transfer. Conversely, entropy decreases with negative heat transfer. So when you have heat transfer going out of a system, the entropy is decreasing. So the direction of entropy transfer is the same as heat transfer. Great. All right, in an internally reversible adiabatic process, it's reversible, so there's no friction, so forth, no irreversibilities, no heat transfer across a finite temperature difference, no internal leakage, no bearing loss, no I²R losses, no irreversibilities, and it's an adiabatic process, no heat transfer. That means entropy must remain constant. So if you have a process that's reversible and adiabatic, even if it's just an ideal process you're doing a mental exercise on to measure the real process against, in turn, reversible, adiabatic applies isentropic. And so you can't have any of those two, reversible, adiabatic, isentropic. You can't have two without the third. And that's called an isentropic process. So we can take that equation back there and solve for dq, and we come up with this TdS equation. And integrating from state one, we can have the Q, internal reversible heat transfer, is equal to the integral from 1 to 2 TdS. So what that tells you is there are many times you can calculate the heat transfer based on the change in entropy, and more importantly, vice versa. So this just shows you that the area under the TS, here's our TS diagram. This time he's plotting total entropy versus temperature. And again, these temperatures are absolute temperatures now, not Celsius and Fahrenheit, but Rankine and Kelvin. So the area under the TdS curve here, process going from 1 to 2, represents the heat transfer. The area under that curve is not work, it's the heat transfer. All right, we're about to be able to get into actually working a couple of numerical examples that maybe bring some of this admittedly very abstract concept into a little more realistic area. Let me see how many slides. I'm on 16. How many are in this? So there are 60. So I need to do about 30, and we'll break it up there. So hope to do that within an hour and 15 minutes. The entropy balance for a closed system can be developed by the Clausius inequality. Remember, the Clausius inequality is one of the corollaries of the second law of thermodynamics. And the second law of thermodynamics sort of says there's no free lunch. In a way, that's what it says. As equation 513 and the defining equation for entropy change, if we define these two equations, we get this nice equation. It's called the second law equation. Or, well, let me back off that. But anyway, it says S2 minus S1 is change in entropy. It's equal for the integral from 1 to 2 of del Q over T, where T is evaluated at the boundary of our system, plus alpha, entropy production. And we'll see how this equation, okay, he says where B subscript indicates the integral is evaluated at the system boundary. In accordance with the interpretation of alpha cycle in the Clausius inequality of 514, the value of alpha in equation 624 has the same meanings. Alpha equals 0, perfect process. No, it's like, I won't say. Perfect process. No irreversibilities, no friction, no heat transfer that causes changes in the atmosphere. That heat transfer is reversible except it causes changes in the atmosphere, and you can't really reverse that. So heat transfer is irreversible. So if it's 0, no irreversibilities are present. If it's greater than 0, that's what happens in all the processes we have going on in the world today. They are irreversibilities. If alpha is less than 0, it's impossible. You've violated the second law of thermodynamics. You've created a perpetual motion machine, and you'll be wealthy as soon as you can get it on the market. That's a joke. No such thing exists. Although a lot of people have thought they made perpetual motion machines, and most of the people who believe they've done that think they've done it with magnets and electricity. Right up you guys' alley, right? Okay, entropy balance for a closed system. Let's see, I should have introduced, whoops, sorry. Page up. Yeah, we're talking about entropy balance of a closed system now, not a controlled volume. And as you see, we've got 5 slides to talk about a closed system, and we're now on slide number 2. Sigma has a value of 0, of course, when there are no internal irreversibilities, and is positive when irreversibilities are present within the system. This leads to the interpretation that sigma accounts for entropy produced or generated within a system by action of irreversibilities. And that's right. Entropy is created and produced by irreversibilities. Friction, internal leakage, I²R losses, all these kind of losses tend to create irreversibilities that actually create entropy. Entropy is like the wind. It's like maybe electricity other than, well, that's not a good one. It's like the wind. You can't see it, but you know it's generated. You know it's there. So an entropy balance expressed in words is just like with internal energy of a system. Change in the amount of entropy contained within the system during some interval, or ds dt, is equal to the net amount of entropy transferred in across the system boundary, accompanied by heat transfer done during some time interval, plus the amount of entropy produced within the system during some time interval. And we can see, by the way, I should have stated for a closed system, like work and heat, entropy can cross the system boundaries, just like heat does. So that's a statement of the entropy of the second law equation, which is the entropy equation for a closed system. All right, let's work a little example here, and maybe these things won't look so abstract. 1 kilogram of water vapor contained within a piston cylinder assembly is initially at 5 bar, 400 degrees C. It undergoes an adiabatic expansion to a state where the pressure is 1 bar and the temperature is 2 levels, A, 200 degrees C, B, 100 degrees C. Using the entropy balance equation, determine the nature of the process in each case. So now we have to actually solve this equation we've been toying with. So we said that this is an adiabatic process, didn't we? Let's see, adiabatic. So the del Q over T goes to 0. So we're just left with S2 minus S1 equal alpha, or on a mass flow, or breaking it down into knowing that total entropy is equal to mass times specific entropy, we can rewrite big S2 as M times small s2. And if we do that for S1, our equation becomes the mass, which is constant for a closed system, times S2 minus S1 is equal to alpha. Now we can actually look up these values. So we know that the mass is 1 kilogram. Let's see. S1 for 200 degrees. Let's see if he pulls up the tables. Well, he looks it up for A. All right, A is 5 bar and 400 degrees C, and it is water vapor. Water vapor. Let's see if we can find that on the table. Water vapor. I'm gonna have to write that down. Where 5 bar, 400 degrees C. Give you a little practice on the tables. Now, I want to make sure you see that. Yeah, you do. All right, let's look at our tables. We want to look at saturated water, and we're looking at 400 degrees, 5 bar and 400 degrees. All right. We looked at pressure table 920. Something doesn't look right about that. 929. All right, let's go down to 5 bar. Sorry. All right. We're going to look for SG. We look in this column. Won't be able to see the column when I roll down far enough, but let me try with my finger here. All right. Let me get my pen out and see. Nope, that didn't work. So I know this hands, there's 5 bar. What did it say? 400 degrees. Oh, I got to read that problem again. I'm sorry. Water vapor. It didn't say it's saturated vapor. Sorry. It's just water vapor. It's probably superheated vapor. Of course it is. 5 bar. What is the first one? Yes, S1. We're looking for S1. 5 bar and 400 degrees. So we need to go on down to 5 bar and 400 degrees. There's 5 bar right here, 400 degrees. So 7.7938 is S1. Let's see if he got that. There it is right there, 7.78. So adiabatic expansions to a state where it is 1 bar and 200 degrees. That's an expansion, so I would think it'd stay in the superheated state. 1 bar and 200 degrees. All right. Okay, there's 1 bar, 200 degrees. So S2 is 7.8343. There it is, 7.7343. So sigma is S2 minus S1 is 0.045405. All right. Sigma is positive. Let's see what that says about that process. Sorry. So sigma is greater than 0, so irreversibilities are present within the system, but that's the kind of process you have every day. So A is a good, valid process. Now let's look if we go to 100 degrees. So now let's go find S2 at 100 degrees. So let's tab over to that, 100 degrees. Did it say, or what the pressure? 1 bar, 100 degrees, okay. 100 degrees, 1 bar, 7.3594 is what I see right there. Oh, S2. Let's see, am I looking at that wrong? S, 100 degrees C and 1 bar. 100 degrees C, 1 bar. 100 degrees C and 1 bar. 1 bar. Okay, 100 degrees C. 7.3614. Yeah, okay, that's what he got. 7.3614. Now, if we calculate sigma, we get negative. And so that, if we look back at our little rule table here, back a couple of slides, if we get a negative value greater than 0, that's impossible. So what that says, that process B cannot take place. It is impossible to reduce entropy in an adiabatic expansion. So the last one of these, more about the expansion B. Okay, we've already talked about it. Since sigma cannot be negative and the expansion B delta S is negative, then by inspection, the integral must be negative. And so heat transfer from the system must occur. What they're saying, in order for that to be true, you have to have some heat transfer. It has to create some negative entropy. So it has to go from the system, heat transfers from the system. So your process, and really to exist, has to have irreversibilities that create heat transfer. All right, entropy rate of change for a closed system. Take a sip of coffee here. I think we're about 20. We need to finish about 10 more slides and we'll stop and I'll finish the rest of it. And then the second part of the lecture, you know, I may wait to do that second part video until I get your homework set up. And then the second part of this chapter is the one I really want to emphasize because it's control volume systems, which are really the real world systems that you're going to deal with as power engineers, if any of you become power engineers or whatever you become. All right. So anyway, back to slide 21. Entropy rate balance for a closed system. That's if we're going to have heat transfer, I believe. Let's see. On a time-based rate basis, the closed system entry rate balance is ds dt equal the sum of the Q dots over T. That's like Q1 over T1 plus Q2 over T2, etc., plus sigma, where ds dt is the time rate of change of entropy of the system. Q dot J over Tj is the time rate of entropy transfer through the portion of the system boundary, whose Tj, and that's transferred by heat transfer. And sigma is the rate of entropy production due to irreversibilities. And sigma is always equal to 0 or greater than 0. Entropy is always produced. If it's equal to 0, it's a fully reversible process, and no such processes exist. If it's less than 0, entropy is decreasing. No such process can decrease entropy. There's never been one developed by man that decreases entropy. All right, let's go on. Got 3 of these slides in this little batch to go through. All right, here's a good one. Here's a good where we numerically apply all of these fancy looking equations. An inventor claims that the device shown generates electricity at the rate of 100 kilojoules per second, while receiving heat transfer of energy at a rate of 250 kilojoules per second from a temperature reservoir of 500 K, receiving a second heat transfer, that's a second heat transfer coming in, at a rate of 350 kilojoules per second from a temperature source of 700 K, and discharging energy by heat transfer at a rate of 500 kilojoules per second at a temperature of 1000 K. Each heat transfer is positive in the direction of the accompanying arrow. Well, that's true, but if we use our heat transfer polarity, where heat transfer in is positive, heat transfer out is negative, we get the same as the arrows. All right, so the problem ends by saying, for operation at steady state, evaluate his claim. All right, so let's apply this equation right there. Okay, but applying the energy rate balance equation. Okay, now this is the first law equation. Remember, dE dt, so there's no change in internal energy. dE dt is equal to 0. So that's equal to Q, sum of the Q's minus the work. So we can solve for the work of that system using the first law equation. Okay, the reason that dE dt is 0 because it is at steady state. Okay. So we know these Q's, Q1 was in Qn 250 kilojoules, Q2 is in at 350, and Q3 was out at 500. So you add all those together algebraically and you get 100 kilojoules of work. And it's plus work, so it's work coming out of the system. So the first law of thermodynamics, first law, doesn't tell you anything's wrong. So the claim is in accord with the first law of thermodynamics. Now applying an entropy rate balance. Now we're at steady state. So we apply this equation here. And of course, ds dt is going to be 0, and these are going to be the sum of the Q's over the T's. So ds dt is 0, it's at steady state. And we got Q1 over T1, and Q1 is positive, so it's a plus Q1 over T1. Q2 is positive, and it's a rate, by the way, Q dot. Q2 over T2, all of them are rates, positive. But Q3 was an outgoing heat transfer, so it's negative. So you've got all the heat transfers and you got all the temperatures, so you can easily calculate alpha. and alpha is equal to minus 0.5 kilojoules per second per K. So we're actually decreasing entropy. We're pulling entropy in somehow. And as we know, the second law says you cannot decrease entropy in a thermodynamic process other than by heat transfer, by the way. But if you add up all the heat transfers, some of these increase entropy, some of them decrease. But if you add it up for the whole process, the sigma has got to be less than zero. If it is less than zero, less than zero is impossible. So you could say that his claim is invalid. It violates the second law of thermodynamics. Now we're going to get to control volumes. What slide we're on? We're on about 24. We'll do a few of these, and it's probably been about 40 minutes. You know, this may be a good place to stop. I think we'll stop right here with this lecture. Entropy rate balance for control volumes, and pick up at this point. So I will make this other video shortly and post it and let you know when it's posted. Probably between these two postings, I'm going to work on your homework for chapter 6. I'm going to put a lot of effort in it because I want it to be interesting in real world system. So I'm signing off. I hope all of you have a good day, and I will see you later.